Welcome to chapter 6.1, where we're going to look at inverse circular function or inverse trig functions. Inverse functions are a confusing bit, so we're going to do a bit of review from algebra, and then we're going to walk through these. There's some confusing bits in here, so just take good notes, put pause when you need to, and this is a little bit longer of a lecture. It's probably going to be a little bit over 30 minutes. Okay. Just moving on. So remember that in math, we define a function as being something that's consistent. That means every time you put the same input or x value into the function, you get the same y or output element or value out of it. Remember, the x or the input represents the domain. All the input values are the domain. And the y value, or f of x, functional notation, all of those y values are called the range. Okay? Sometimes it's necessary if we don't want the output values to be used more than once. We want there to only be one time when you can have an output value. We can limit the range so that each input uses one and only one output y value, and then this is called a one-to-one function. Okay, so while every time you put an input in, let's say for example when you go to pump gas, if gas price is $2 a gallon and the function of the pump is to calculate what you owe for the gas you pump, when you pump 10 gallons of gas, you expect that function to be consistent so that every time you pump 10 gallons, you pay $20. If it acted like a slot machine, sometimes you pump 10, you'd pay 20, sometimes you pump 10, you'd pay 300. Then it's not a function because it's not consistent. In that example, the 10 gallons is what you pump every time, and you want that value, that output value of 20 to be the same every time you pump 10 gallons. There are some functions where different inputs can have the same output value. For example, if you have a data plan on your cell phone that limits your data, let's say you pay $30 a month for a 5 gigabyte data plan. If you use 1 gigabyte of data, you still pay $30, so the input would be 1. If you use 2 gigabytes of data, you still pay $30, so the output for 2 is also 30. The output for 3 is 30, the output for 4 is 30, the output for 5 is 30. This is an example of a function that is not one-to-one, okay? So a function can have the same output for different input values, as you just saw. For a 5 gigabyte data plan, any data that you use up to 5 gigabytes, you're going to pay the same thing. So all of those outputs would be the same. So sometimes we change the domain and range so that we can make a one-to-one function. Now, why do we do that? We do that because in order for a function to have an inverse function, it has to be one-to-one. Functions that are not one-to-one do not have an inverse function. Okay? Inverse functions, this is just reminding us about an inverse function. This is the notation f to the negative 1. It is not an exponent. We read this as the inverse of f of x. This says that the inverse of f of x is equal to yx. The coordinated pairs, the ordered pairs, are the opposite as they are in the function. Because remember that the way you figure out what an inverse function is, you turn x's into y's and y's into x's, and this gives you the inverse function. For example, if the point 2, 3 is in the function f of x, then f inverse of x will have the point 3, 2. The x value of 2 becomes the y value in the inverse, and the y value of 3 becomes the x value in the inverse. And again, as I said, f to the negative 1 is not an exponent, it's just notation. and it's read as f inverse of x. In a one-to-one function, each x value corresponds to one and only one y value. There is no shared y values. If a function is one-to-one, then it has an inverse function, f inverse of f. The domain of the function is the range of the inverse. This is just saying the x values of the function become the y values of the inverse. And the range, the y values of the function, become the x values of the inverse. This is what we were just talking about. X becomes y and y becomes x. And if you look at the graph of the function and its inverse, these are reflections of each other across the line y equals x. This is the diagonal line from the lower left to the upper right of a graph. And that line becomes like a mirror so that on each side of it you see a reflection of that graph. Okay? Using the knowledge we just talked about, we can figure out a formula for a function, and we can figure out the formula for the inverse if we're given a formula for a function. Okay? So what are we going to do? All right, the first thing we're going to do is we're going to rewrite the function, the functional notation in terms of x and y. So we look at x and y pairs on a grid. So we're going to change f of x into y. Okay. Now we have, instead of f of x equals 4x plus 2, all we've done is replaced f of x with y. Y equals 4x plus 2. The next thing we're going to do is we're going to interchange x and y. Wherever we have a y, we're going to make it an x. Wherever we have an x, we're going to make it a y. And you can see that here. Okay? Because that's how we get the inverse function. X becomes y and y becomes x. Then we're going to solve this new equation with the transposed variables for y. We're going to subtract 2 from both sides, then we're going to divide both sides by 4, and we get y equals x minus 2 over 4. Once we're at this place, the last thing we do is we replace y in this new equation with our functional notation for the inverse. So all I've done here is replace y with f inverse of x. Okay, and this is the formula for our new inverse function of f of x. So again, replace f of x with y, change y into x, change x into y, solve for y, and then replace y with the inverse notation. Very simple and straightforward. These are good graphs to kind of, again, show you the relationship. So if I have a point a, b on a function, then its inverse function would have the point ba. The x becomes the y becomes the x. Okay, and here you can see a graph. Instead of just a point, you can see the graph and the formulas here, and you can see that, again, they are reflected across this diagonal line, which is y equals x. All right, so let's get into our inverse trig functions. We read this as y equals the inverse sine of x. In trig functions, we can also use the notation or the language of arcsine. Arcsine is the exact same thing as inverse sine, okay? And it's arcsine, arctangent, arccosine, etc. Arcsine just simply means the inverse of that trigonometry function, okay? If we have y equals the inverse sine of x, what this actually means is that x equals the sine of y. So move this over to the other side, okay? X equals the sine of y. Because all of the trig functions are periodic, we have to limit their domain so that we can have one-to-one functions, so that indeed we can find an inverse function. Notice that the angles for sine go between negative pi over 2 and pi over 2, which means that whenever we're solving for inverse sine, we're looking for values in either quadrant 1 or quadrant 4. Okay? And the way to think of this is y is the angle in the interval negative pi over 2 or pi over 2, or y is the angle in quadrant 1 or 4 whose sine is x. Y is the angle in quadrant 1 or quadrant 4 whose sine is x. So let's do a problem. Find y in the equation. I think it's easier to quickly rewrite these in terms of sine or their trig functions, not their inverse sine functions. So notice here we could rewrite this as the sine of y equals 1/2. Y equals the arc sine of 1/2. This is the same thing as the sine of y equals 1/2. Okay? Now we're in, again, quadrant 4 and quadrant 1. And since we're positive, this has to happen in quadrant 1. Okay? This is a known angle. Think of our 30, 60, 90 triangle, how we built that. And specifically, the sine of pi over 6, or 30 degrees, is equal to 1/2. Sine is equal to opposite over hypotenuse. And if you built that triangle, you would see that that's a 30-degree angle, or pi over 6. So we get the sine of pi over 6 equals 1/2. And so y is equal to pi over 6. Okay, this is in quadrant 1, so we're fine for this answer. We do have to make sure we're in the right quadrant, and if we're not, then we have to use the angle we come up with as a reference angle and calculate the new angle in the specific quadrant. Okay, y equals the inverse sine of -1. Here we're going to do the same thing. This is the sine of y equals -1. Again, we are in quadrant 1 or quadrant 4. This is actually in quadrant 4 because it's negative. Sine is negative in quadrant 4. And it's at a quadrantal, specifically negative pi over 2, or 270 degrees. And so y equals negative pi over 2. Notice we would not use 270 degrees because it's not in the domain or the range of y given here. Y equals the inverse sine of -2. This is again saying that the sine of y equals -2. And remember that the sine cannot equal a number outside the interval of -1 to 1. So this is impossible. So this doesn't exist. Again, this is saying the sine of y equals -2. And we know that sine only goes between 1 and -1. In these kind of problems, if you were using your calculator, you would get an error message. When you use your calculator, also be sure that the number given for an inverse function is in the range of the particular inverse function being considered. For me, it's easier to think in terms of quadrants first than to just think in terms of that range. So thinking, is that number inside the quadrant that it should be in? All of the inverse trig functions have two quadrants, a positive and a negative, so you just have to figure out which quadrant you're dealing with. You can pause here and look at this. This is just giving you kind of an overview of the range and the graph of all the inverse sine function. Y equals sine inverse of x, or y equals arc sine x. If you looked at that graph on the previous page, you saw it was increasing and it's continuous. Its x-intercept is 0, its y-intercept is 0, so it's going through the origin. It's symmetric with respect to the origin, you can see that, which means that it's an odd function and that the inverse sine of a negative angle is equal to the negative inverse sine of that same angle. Okay. By the way, I'm not so hung up on all that data, etc. But the calculations, the problems are very key. So let's move on to inverse cosine. We have y equals inverse cosine of x, or y equals arc cosine. And again, as I said, arc cosine is just the naming for inverse of the trig functions. Arc cosine, arc tangent, etc. They mean exactly the same thing. And again, I think the easiest thing is to rewrite these quickly. This can be rewritten as the cosine of y equals x. The cosine of y equals x. Okay. Or another way to think of this is y is the angle whose cosine value is x. Okay, for cosine, we're dealing between 0 and pi, so we're in quadrants 1 and 2. In quadrant 1, cosine is positive. In quadrant 2, cosine is negative. Find y in each equation. Again, I think it's best if we quickly rewrite this as the cosine of y equals 1. And where does the cosine of y equal 1? Well, cosine is the x value on the unit circle, and so this is at the very beginning, the origin, so the angle is 0. The cosine of 0 equals 1, so y equals 1. And we're in quadrant 1. We're really between them, aren't we? Because it is a quadrantal. Let's get another problem. Y equals the inverse cosine of negative square root of 2 over 2. So this is saying the cosine of y equals negative square root of 2 over 2. So we know we're in quadrant 2. So what we're looking for is the reference angle for quadrant 2 and then define the actual angle. Okay, so the cosine of y equals negative square root of 2 over 2. This is again is a known angle from the 45, 45, 90 triangle. Specifically, we know that the cosine of pi over 4, I don't really like how they've done this because they've jumped right into the answer here, okay? I'm not sure if your calculator would give you this answer directly or if it would give you the reference angle, okay? Well, the reference angle is pi over 4. Well, if the reference angle that gives us square root of 2 over 2 is pi over 4, remember in quadrant 2, this means I have to subtract that angle from pi or from 180 to actually get the angle. So pi minus pi over 4 gives me 3 pi over 4, which is our solution there. I think they're skipping a few steps here. I think it'd be better if it was visual. I think it's better to think of these in terms of known angles, 30, 45, 60, and then use the reference angles and figure those out. Again, you can see the graph here, the domain and range, etc. I'm not going to go through this information. It's not quite as important. And it's decreasing. It's continuous. You see the x-intercept is 1. The y-intercept is pi over 2 or 90. And the graph is not symmetrical at all. It's not symmetrical with the y-axis nor the origin, etc. All right, moving on to tangent. Here we have the, inverse tangent. Y equals the inverse tangent of x, or y equals arctan of x. Tangent, much like sine, is in quadrant 1 and quadrant 4, negative pi over 2 to 2. Okay, we can see it's continuous. It goes through the origin. It's increasing, it's continuous, its x and y intercepts are 0, so it's going through the origin. It's symmetric with respect to the origin, so it's an odd function. And of course, for tangent and cotangent, we have horizontal asymptotes for inverses. And again, y equals the inverse tangent of x is the same thing as saying the tangent of y equals x. Y equals inverse tangent of x, the tangent of y equals x. It's important to get that in your head so that you can solve these problems without getting confused. Similarly for inverse cotangent, here we are in quadrant 1 and 2, 0 to pi, just like cosine, okay? And y equals inverse cotangent of x is the same as cotangent of y. Cotangent of y equals x, y equals the inverse cotangent of x. Here we have secant, y equals the inverse secant of x. And we are in, again, secant is the reciprocal of cosine, so we're in quadrant 1 and quadrant 2. Cosecant is the inverse of sine, so we're in quadrant 4 and quadrant 1. To me, the biggest thing about this chart is remembering the quadrants that each thing is in. Okay, sine, cosecant, and tangent 1 and 4, cosine, cotangent, and secant 1 and 2. This is really important when you're solving problems with inverse trig functions. Okay. Theta equals arctan 1. Okay, what does this mean? This means the tangent of theta equals 1. Since 1 is positive, this has to be in quadrant 1 because tangent is in quadrant 1 and quadrant 4. Tangent is positive in quadrant 1, where sine and cosine are both positive. Tangent, which equals sine over cosine, is going to equal 1, where the sine value is the same as the cosine value. This only happens at an angle of 45 degrees, or a reference angle of 45 degrees. Since we're doing degree measures here, then the tangent of theta equals 1 gives us that theta equals 45, because the tangent of 45 is indeed 1. Okay. Here we have theta equals the secant, the inverse secant of 2, which is saying that the secant of theta equals 2. Secant is the reciprocal of cosine, and so we're in quadrant 1 and quadrant 2, and since 2 is positive, we are in quadrant 1. So we get the secant of theta equals 2. We can plug this into our calculator, and indeed we would get, actually we can't plug that into our calculator. So how would we solve this? This is a good question. Well, remember the secant of theta is the reciprocal of cosine. So the cosine of theta would equal the reciprocal here, or 1/2, which is a known angle from our 30, 60, 90 triangle, specifically the 60-degree angle. Typically when I'm dealing with secant and cosecant, I'm thinking in terms of sine and cosine, and specifically the reciprocal functions. Find y in radians if y equals the inverse cosecant of -3. We'll make sure your calculator's in radians because it tells us to use it in radians. Then we enter y equals cosecant y equals the inverse cosecant of -3. As remember, cosecant is the reciprocal of sine, so we use the inverse sine button. It's right above the sine button, so use the second button on your calculator. And then we take the reciprocal of this angle, of this value, and so it's negative, instead of 3 over 1, we get -1 over 3. Inputting that into our calculator, we get -0.3398, which is somewhere in quadrant 4. Okay. Find theta in degrees if theta equals arc cotangent -0.3541. Again, here we have, we're going to use the calculator, but we don't have a cotangent button. We're going to use the tangent button, the inverse tangent button. And so we do, blank there, inverse tangent of 1 over -0.3541, since cotangent and tangent are reciprocals. Now this is a special weird case. Whenever you're doing an arc cotangent of a negative angle, okay, remember that this would mean that we are in quadrant 2, okay, because the cotangent is negative in quadrant 2. But since we're using our calculator, the negative tangent value, the negative inverse tangent value, will be in quadrant 4. So we always have to add 180 degrees, or pi, to our answer. So this problem, what we're going to do is take the inverse tangent of 1 over -0.3541, and then we have to add 180 degrees because this answer is going to be in quadrant 4. And we want to be, for cotangent, because of our limitation on the domain and range, we have to be in quadrant 2. So specifically for arc cotangent values that are negative, remember to add 180 degrees. And that's what this is all saying that I just emphasized. All right. let's look at some unique problems here where we're looking for the sine of an inverse tangent of 3/2, okay? So if we think of this whole value in parentheses as theta, we get theta equals the inverse tangent of 3/2, or the tangent of theta equals 3/2, okay? Well, what we want to do here is we want to find the sine of theta, right? Because this whole value is theta. Well, here we have 3/2, the tangent of theta. Tangent is in quadrant 1 and quadrant 2. Since this is positive, we're in quadrant 1. So let's graph this in quadrant 1, recognizing that tangent values are the opposite over the adjacent. So the opposite is 3. Opposite theta is 3, the adjacent is 2, and we can find the value of the hypotenuse by using the Pythagorean theorem. A squared plus b squared equals c squared, and then solving for c, if you will, or the hypotenuse. Once we have the triangle figured out, the sine of theta is easy because sine equals the opposite over the hypotenuse. So we can easily plug those values in. We get 3 over the square root of 13, or of course, multiplying the numerator and denominator by square root of 13. To rationalize this, we get 3 times the square root of 13 over 13. So why don't you try this one, doing the same way, figuring out what quadrant you're in for the inverse cosine, create theta equals this, build your triangle, and then find the tangent value by opposite over adjacent. So hit pause and you can do that to make sure that you've got it. They're pretty straightforward and they're kind of an interesting problem. So again, we're going to set theta equals inverse cosine of negative 5/13. So the cosine of A equals negative 5/13. Since we're negative and cosine is in quadrant 1 and quadrant 2, we're in quadrant 2. So let's build our triangle in quadrant 2. Cosine is adjacent over hypotenuse, and we're talking about this little angle inside because we're talking about a reference angle. So the adjacent angle, you can see where my little red dot is, the adjacent angle is negative 5, the hypotenuse is 13, as we saw there. So again, we can find this value of the other side as a squared plus b squared equals c squared, or negative 5 squared plus y squared equals 13 squared, and then simplify that. All right. So now we can see that since this is the angle, we're looking for the tangent, which is opposite over adjacent, or 12 over negative 5. Very simple to do these, and they're kind of an interesting problem. They can also be interesting in that they might involve identities. Notice here we have two inverse functions. We have arctan and arcsine. So really we're taking we're looking for the cosine of the sum of two angles. And if you remember your identities from chapter 5, we have the cosine of a sum. So we're going to use that to solve these. We're going to do this just like we did in the two previous examples, but we're going to have to do it twice. We're going to have a graph for arctan square root of 3. We're going to have a graph for the arcsine 1/3, and then we're going to figure out those angles and then plug it into our cosine of a sum identity. Okay, so if we let A equal arctan square root of 3, then we get tangent of A equals the square root of 3. Tangent of A equals square root of 3. If we let B equal arcsine 1/3, then we get the sine of B equals 1/3. Okay. Tangent is opposite over adjacent. There's not a fraction here, so put it over 1. Tangent is positive here, so it's in quadrant 1. Sine is also in quadrant 1 because it's positive. So both of these are going to be triangles in quadrant 1. A is going to be the square root of 3 over 1. And again, tangent is opposite over adjacent, square root of 3 over 1. We can find the other angle by 1 squared plus the square root of 3 squared and taking the square root. So we get all three sides. And the sine of A is going to be opposite over hypotenuse, square root of 3 over 2. And the cosine of A is going to be adjacent over hypotenuse 1/2. We're going to do the same thing with B. We're in quadrant 1. The sine is opposite over hypotenuse. So we draw this in with B, the opposite 1 over the hypotenuse 3. Again, we calculate this x value, or the base value, by a squared plus b squared equals c squared. I'm not going to go through that again. And we can see here we were already given the sine of b equals 1/3. That was a given. But the cosine of b is the adjacent over the hypotenuse, which is 2 times the square root of 2 over 3. Now, why do we want all those? Because of the cosine sum identity. Remember that the cosine of a plus b is cosine A, cosine B, minus sine A, sine B. So we needed all of these values, sine of A, cosine of A, sine of B, cosine of B. And now all we have to do is plug them in and simplify. Okay, so it was a bit involved. We broke it down. Whenever we have these inverse angles, we're going to draw it so that we can then take the trig function of, using the relationship values of like opposite over adjacent, SOHCAHTOA, as we learned earlier in the course. Okay. Notice here we have the tangent of a double angle. So we're going to be using, again, look for these things that here we have 2 times an angle. So our theta is going to be arc sine 2/5, and then we're going to use the tangent of a double angle identity to solve this problem. Okay, so b equals arc sine 2/5, so sine of b is 2/5. This means we're in quadrant 1. Sine is opposite over hypotenuse, so we're going to sketch this opposite over hypotenuse. Find out the other side. Again, a squared plus b squared equals c squared. We can then find the tangent of b, which is opposite over adjacent. Sorry, that's the identity. The tangent of b is the opposite over the adjacent, or 2 times the square root of 21 over 21 when we rationalize. And then we use the double angle identity. The tangent of 2b equals 2 tangent b over 1 minus tangent squared b. Again, noticing both of these use tangent of b, which we just figured out. So all we have to do is plug these values in and then keep simplifying. Okay, I'm not going to go through this complex fraction simplification. You should be able to do that by now. Okay, so we have one more thing that we're going to look at here, and this is a word problem. And this says the optimum angle of elevation theta, and you can see theta there in the diagram, that a shot putter should aim for in order to throw the greatest distance d on the velocity, depends on the velocity v of the throw and the initial height of the shot when he releases. Okay, a formula for this that achieves the greatest distance is theta equals arc sine of the square root of v squared over 2v squared plus 64h. This is actually quite a simple problem because it gives you the formula, and it's going to actually give you the values to input into the formula. So if we want to find the angle, all we have to do is substitute 6.6 in for h and 42 in for v in these two places. And so this is really a rather simple problem. It looks confusing, but this is what I call a plug and play problem. And if you get this on the test, you should be really happy. So this